Hello, my name is Guillermo Castilla and this is AULA UE. We're going to start talking about continuous distributions. Now, a continuous distribution is very similar to a discrete distribution, but of course, in this case, it describes a continuous variable, which means that it has infinite values between one value and the next. Okay, so for example, if we had a domain, continuous domain defined between a and b, and we had this density function I'm doing here, this would be f of x. If we wanted to know the probability between two values, alpha and beta, inside this domain, well, that probability would be a bit hard to calculate. Let's say that we have a random variable chi, and let's call our domain, I don't know, let's call the whole domain from a to b of gamma, capital gamma. Okay, so the probability of chi of being between alpha and beta, so alpha being smaller or equal than chi and smaller or equal than beta, would be, of course, the integral from alpha to beta of my density function f of x differential of x, which is actually quite a pain to calculate. It's a bit difficult. And we know that the result of that integral would also be the area below the curve. So that would be the area below that curve from alpha to beta. And, well, even if integration isn't our strong point, it still is a bit uncomfortable to calculate. So the good thing about continuous models is that we can forget about integrating forever. We're going to talk about the main model we're going to study, which is the normal distribution. The normal distribution model is defined by two variables. We know that most models need a certain variable distribution. In this case, the variable we need to know is mu, which is the mean of the population we're modeling, and sigma, which is the standard deviation of the population we're modeling. Now, the normal distribution is called normal because it's the most normal thing you can find in nature. So, for example, the height of a person, the weight of a certain species of animal, the growth of a tree, all of these naturally distribute through this continuous model known as the normal distribution. It's symmetrical and it's centered around the mean of the population. So, as you know, the probability is the area below the curve, so you can see that most of the probability goes around the mean, and it gets scarcer, it gets less as you go to the sides, as you get away from the mean. It is a continuous variable, and it's defined between minus infinity and infinity. So the thing is, it's so improbable when you're close to infinity or minus infinity that it practically tends to zero. It does follow, on the other hand, the Chebyshev law, which means that the probability of being in an interval that is one standard deviation away from the mean to each side is around 67%. If we go two standard deviations to each side of the mean, we have a 95% of probability. And if we go three standard deviations to each side of the mean, we get all the way up to a 99. Actually, it's a 99.9% of probability. So, well, it's good to know how the normal works. And we really don't need to integrate anything. It does have a known distribution function, and it also has a known density function, but we're not going to study any of them because we don't really need them. The whole variable can be studied through tables and charts. So we'll see later on in a further video how that's done. So let's see the other two variables that might be interesting in continuous models, although we're not really going to use them in problems, not yet, just yet at least, which would be the t of student and the chi squared. As you can see, the t of student is a continuous variable that looks very much like a normal, only it's centered around the zero, so the area to each side of the zero is the same. Just like in the normal, the area to each side of the mean is exactly the same. That is because the t of student actually comes from a normal. On the other hand, we're also going to study this chi square, which has this hump on one of its sides, and is no longer symmetrical. It's chi square of n. As you can see, both the t and the chi square both depend on n, which is the number of distributions we're taking in hand. It's the size of the sample. Okay, and that really depends on, and they both come from a normal. This x in the t of student goes from minus infinity to infinity, as the normal does, and in chi square of n, the x goes from 0 to infinity, as you can see there on the chart. So this is the t of student. This other one is the chi square. Chi from the Greek letter chi, that's that big capital X kind of shape you have there, is a chi really, and this is the normal distribution. So the main thing we're going to study really is this normal we have there, and the t of student and the chi square are also important, but they'll be much more important later on in inference. For now, we just have to know that they come from a normal distribution, and it's well, it's marginally interesting that we actually know they exist. So I hope you like this introduction to continuous models, and we'll see you around here on AULA UE.